Yeah, the search for the right pen. It's always an ongoing search. Actually, I like these. My one I gravitate to at the moment is the Sharpie S Gel.
Oh, that's what I have.
Yep, I like these. They're pretty good. Oh, you don't like them?
The enjoy paper mates. Very cheap.
Hmm.
Roll off.
I see. Uh-oh.
Maybe I should get a feather and ink.
Uh-oh. I am, for reasons they're hard to explain, as you know, I'm coaching basketball at the moment, and like, I think half the elementary school is sick with the Omicron or whatever. So of course this impacts the basketball. Like half of Isaac's team is sick, and 2 of my 6 players are. So I don't know. Anyway, let's talk about math. So section 3.2, 13.2 rather, is on algebraic extensions. Let's straight into it. Definition. Alpha and K is algebraic over F if alpha is root of non-zero f of x non-zero polynomial with coefficients in f. All right. If alpha is not algebraic over f, then it's said to be transcendental over f, and the extension k over f is said to be algebraic if if every element of K is algebraic over F. All right, so again, transcendental over F means that it's not algebraic over F. I didn't write it down, but I said it. Proposition 9. Says that if let alpha be algebraic over F, all right, then there exists a unique monic irreducible polynomial, which we'll call m sub alpha comma f of x. So it's got coefficients in f, all right, which has alpha as a root. And moreover, f of alpha equals to 0 if and only if m alpha comma f of x divides f of x. All right, for f of x and for a polynomial with coefficients in f, okay? It would probably be wise for me to go through the proof of this because we haven't gone over that material yet this term. So let me actually slug through the proof of proposition 9. All right. So he's like, let g of x be polynomial of minimal degree such that g of alpha equals to 0, right? So we can modify g by dividing by its leading coefficient to make it monic, right? So you can assume, we'll assume g of x monic, divide by g of 0 if needed. I'm not g of 0, I'm an idiot. Anyway, we can assume g of x is monic, so divide by the leading coefficient if needed. All right, fine. All right, so suppose g of x were reducible. Suppose g of x is equal to a of x times b of x, right? Where the degree of a of x and the degree of b of x are less than the degree of g of x, right? Suppose it were reducible. Then what? Then you'd have g of, g of alpha would be a of alpha, b of alpha, right? Which would say what? There's a polynomial of lesser degree, which takes alpha as a 0, right? But that would contradict the construction of g of x. Therefore, but this, this contradicts the construction of g of x. So what do we get? Thus, g of x is irreducible. So what was proposition 9? Alpha algebraic over x. There exists a unique monic irreducible, right? Let's continue on here. So he says, it follows that g of x is a monic irreducible polynomial having alpha as a root. Suppose now that you have f of x is any polynomial having alpha as a root, right? So next stage in the proof, let's let f of x be a polynomial with coefficients in f such that f of alpha equals to 0, all right? By division algorithm, there exists r of x, right, in f of x such that r of x equals to 0, or r of x, or the degree of r of x is less than the degree of g of x, and q of x in f of x such that f of x is equal to q of x times g of x plus r of x, right? This is the division algorithm for f of x divided by g. So then what? Observe that f of alpha, right, is q of alpha, g of alpha, plus r of alpha, right? By the usual rules of the evaluation map. But we know g of alpha is 0 by assumption, right? So this is just equal to r of alpha, which is equal to 0. If r of x is non-zero, then that would give you a polynomial of lesser degree than g, which takes alpha as a 0. This is forbidden by the construction of g. Therefore, it must be that r of x is equal to 0. So this implies r of x is equal to 0. And hence, what do we got? F of x is equal to q of x times g of x, right? Which means that that minimal polynomial of alpha over f of x divides f of x as required. So of course we're identifying that this is the minimal polynomial over f of x, right? And this is our notation for this g of x. Corollary 10. Corollary 10 says that if L over F is an extension of fields and alpha is algebraic over both F and L, then the minimal polynomial of alpha over F, with respect to L of x has to divide the minimal polynomial of alpha over F of x. He said this is immediate from the second statement in proposition 9 applied to L, since m alpha comma f of x is a polynomial in L of x having alpha as a root. Right. So let's see, an example of that would be something like, let's see here. Here's a really simple low-tech example of that. We could take the real numbers over the rational numbers, right? Real numbers are an extension of the rational numbers. And they're both fields, obviously, right? And take alpha equal to the square root of 2. So the minimal polynomial of alpha with respect to the rational numbers is x squared minus 2. That's irreducible by Eisenstein criteria. All right. But of course, the minimal polynomial of this with respect to the real numbers is just x minus root 2. That takes square root of 2 as a 0, of course, right? And as you can see, x minus the square root of 2 divides x squared minus 2 in r of x. So the complete statement of corollary 10 was this was in L of x. I just didn't write it, but it's in the extension field that the divisibility occurs. Make sense? So, mhm.
The only thing I have a question over is when we're constructing this g of x, and for when we're proving prop 9.
Mm-hmm.
So we have g of x, a polynomial minimal degree, such that g alpha is equal to 0, and assume gx is monix. Suppose that gx is divisible or factorable,
Mm-hmm.
and the factored polynomials have less degree than g of x, which is kind of intuitive.
Right.
Um,
Well, that's what's needed for it to be a reduction, right?
mhm.
Yeah.
Okay, and so that follows that if g of x, g of x is a factorable, that the factoring polynomials would also have the same 0.
Well, one of them, at least one of them has to have a 0. I don't know which one. It could be that A has the 0. It could be that B is 0. But we have the product of two things in a field 0, so one or the other of them has to be 0.
Yeah.
Or both.
Yeah.
But
And,
yeah.
So this is a contradiction over, like, because why?
Because G was the polynomial of minimal degree such that G of alpha was 0.
There it is.
And that's the same thing that contradicts the R being non-zero.
Yeah. I knew they were the same argument, that's why I was like,
Mhm,
okay.
mhm.
Okay. Minimal degree of alpha.
Right, exactly. So, definition, the polynomial is this m alpha f of x is the minimal polynomial of alpha over f. And the degree of m alpha of x is the degree of alpha is understood to be the degree of m alpha comma f over x, okay? And proposition 11 says it's also equal to, that this is equal to the dimension of the extension of f by alpha. So this is what I wrote in yellow just now. That is proposition 11. Like proposition 11 says essentially this, that f of x mod the ideal generated by the minimal polynomial, right, is equal to, well, it's not equal to, it's isomorphic to f adjoint alpha. And the degree, again, the degree of alpha is the dimension of f alpha over f. Yeah, that's just colon, not semicolon, my bad. Colon. So,
So why do we need a degree for an algebraic number? When we're just referring to the degree of the monic polynomial that it solves, the minimal polynomial that it solves.
well, there's, different minimal polynomial for different numbers, and, although many numbers of a particular type have the same sort of minimal polynomial, like, 2, 3, 5. So x squared minus 2, x squared minus 3, x squared minus 5. It's kind of the same example, right? But it's not. It depends on the question you ask. We shall see. I got to wash this board with some like degreaser, because when they put somebody would ate a hamburger or something and had greasy fingers and left their greasy fingerprints up here. All right. So, examples. see, I already did. So I'll just write it again here for completeness, but for square root of 2 over rationals, we have m square root of 2 q of x squared minus 2. So the degree of the square root of 2 over q, right, is 2. So see, I think I wrote degree of alpha down there. Like when you write that, it should be that means that
Plus the,
it's under the base field f is understood.
yeah, but you have it, oh well. You have
Yeah. So the square root of 2 has degree 2 over the rationals, but it's got degree 1 over the reals. So the base field in consideration matters. To minimal poly, well, let me just write it down. M of the, I'll use my notation, cube root of 2 over the rationals is x cubed minus 2 rather. Again, that's irreducible by Eisenstein criteria, and so, the degree of the cube root of 2 over the rationals, right, is equal to 3, and that's also equal to the dimension of q adjoin this cube root of 2, right, over q. Oops. Why? Because, as we know, 1 cube root of 2 squared, right, is q basis, right, for q adjoin the cube root of 2. All right, so then his third example is like, okay, likewise, you can see that the degree of the q adjoin the nth root of 2 over q is equal to n, because it's easy to see that the minimal polynomial of the nth root of 2 with respect to q is just given by x to the n minus 2, which again is irreducible by the Eisenstein criteria. But in contrast, right, the minimal polynomial of the nth root of 2 with respect to the reals is just x minus the nth root of 2, right? Because the nth root of 2 is a real number, and that first order polynomial takes it as its 0. And by the way, again, as an example of corollary 11, the x minus the nth root of 2 divides x to the n minus 2, like that's a factor of that. Example 5. This one looks a little bit more interesting. He's got p of x equal to x cubed minus 3x minus 1 over q. He has previously proved that this is irreducible since it's a cubic which has no rational root. Right, you can apply the rational roots theorem here, right? Because you're looking over Q, rational roots theorem tells you whether or not there's a root, right? Because for there to be a root in the rationals, it's got to be a rational root. Kind of inescapable. So that's irreducible. And so what that shows you is that Q, so if, let's see here. For any root, so for any root alpha of P of x, the degree of Q of alpha over Q would be 3. So, I mean, it's just kind of that. So then, so irreducible over Q, which tells us then that if P of alpha equals to 0, then Q adjoin alpha has degree 3 over Q. This particular cubic has like one real root and then a pair of complex roots that are not apparently pretty because he has only described them analytically in the book. All right, so proposition 12. What is Prop 12? Prop 12 is the following. The element alpha over F is algebraic. Excuse me, I'm an idiot. The element alpha is algebraic over F if and only if the simple extension f of alpha over F is finite. More precisely, alpha is an element of an extension of degree n over F, then alpha satisfies a polynomial of degree at most n over F. And if alpha satisfies a polynomial of degree n over F, then the degree of f of alpha over F is at most n. I'm not writing that down. But I will try to look at the proof of this. So he says, if alpha is algebraic over F, then the degree of the extension f alpha over F is the degree of the minimal polynomial of alpha over F. Let's see here. So if alpha algebraic, right, then there exists, right, m alpha comma f of x in f of x, right, such that m alpha comma f of alpha equal to 0, right, and that's the monic polynomial of least degree. And then what? And we know that f of alpha, right, is isomorphic to what? F of x mod m alpha. And we also know that this is equal to, I mean, this is isomorphic to, of course, the span, right? 1 alpha squared, alpha to the n minus 1, where n is equal to the degree of m alpha. In other words, n is the degree of alpha over F, right? And now I'm just using like proposition 11, you know, in the things we did last time that said, you know, if we are quotienting by an irreducible nth order polynomial, then the result is a n-dimensional over F vector space where the 1 and then powers of the root by the number which we're extending all the way to n minus 1 serve as a basis for the extension field as a vector space over the base field, in this case F. All of that is to say that this extension, right, is finite. It's a finite extension, right? Conversely, suppose f over alpha finite, right? with, and we'll let the dimension of it be n again, okay, just to sake. Let's suppose that the dimension is equal to n, all right? So we're supposed to show that there is a, you know, we're supposed to show that alpha is algebraic, right? So if it has degree n, consider this. Then consider, you know, oh, one alpha, alpha squared, alpha cubed, da 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 da, alpha to the, you know, to the n. That is a set of what? N plus 1 elements in f of alpha, right? Therefore, that is a linearly dependent set because it has dimension n plus 1. So that implies that there exist, you know, B0, B1, Bn in F, right? Such that, you know, B0 plus B1F, B1 alpha, B2 alpha squared, Bn alpha to the n is equal to 0. Not all 0, right? So what does this show? This shows that if you look at f of x equal to b0 plus b1x, right? Bn x to the n, this has f of alpha equals to 0. Which shows what? That shows that alpha is algebraic over f because it's the 0 of a polynomial with coefficients from f. Did I make this a question on your test 3 in number theory? It was a question either on your test 3 or the final, and I may or may not have bailed on it. But in one edition of your test, it was a question which could have happened.
I was trying to think, but I don't. Yeah. It was really the coordinate. That was really tough one on that. I remember most of the coordinate stuff.
Uh-oh. I hope I have not done the horrible thing of never panning back to the examples, but I think I did. Pretty sure I did. I think we're okay. Okay, here we go. So, corollary 13, which I should probably try to fit over here, actually. Put it over here. Corollary 13, if k over f is finite, then it's algebraic. Thank you. Oh, you got it. Thanks. Oh, let's see here. So here's the proof. alpha in K, all right, then he says, the subfield f of alpha is a particular subspace of the vector space K over F. Right, so f of alpha is a vector subspace of K. All right. Hence, the degree of f alpha over F, right, which is the dimension of f alpha as a subspace of the vector space K, is less than or equal to the degree of the totality of K over F, right? So what does that tell us? So if K is a finite extension, right, then you pick any element of K, look at the simple extension by that element. Well, that is a subspace of K. But since that is also a subspace, since the dimension of that subspace cannot be more than the dimension of the space overall, this is given to be finite, right? This is given to be finite. It follows that that's also finite. If you can have less than something, right?
If K is already given to be finite, yeah.
So this implies that like the degree of f alpha over F is equal to n for some n, which then by proposition 12, remember what we had, alpha is algebraic over F if and only if the simple extension is finite, right? So that means that alpha is algebraic over F by proposition 12. But notice that alpha was an arbitrary element of K. So we just showed an arbitrary element of K is algebraic over F. That means that the extension K is algebraic. An algebraic extension is one in which every element in the extension is algebraic. So.
Okay.
Yeah, it's not bad, right? Not bad.
So it's essentially like if you already have a field that's algebraic, then the extension field must be algebraic. Like all the elements in the extension field have to be algebraic.
If you have just say what you said again. I didn't quite track. Sorry.
So we have an algebraic field.
Mm-hmm.
And we're extending it out. So that means, wait, no, that's not what you got. You said alpha is algebraic over F.
What this says is if you have a field F, right, and you extend it to an extension field, and that extension field is finite, then that means that every element of the extension field is algebraic over the base field. I believe. K over F is finite, and it's algebraic. I mean, we're saying K is algebraic over F, is what we're saying. That means that every element of K is the zero of some polynomial in F. Maybe it's helpful to see when this is not the case, like sort of a counterexample, if you will. If you, this is kind of ugly, but if you take Q, right, and you adjoin pi, right? Pi is a transcendental number over Q, right? So what this looks like is things of the form, A0 plus A1 pi, dot, 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 dot. So what this actually is, you could look at it like this. It's really polynomials in pi, essentially, right? Oh, I'm sorry, this is the field, so I should say it's rational functions in pi. But anyway, my point to you is this is certainly not, it is not the case that q adjoin pi over q is certainly not less than infinity, right? I mean, it is very much an infinite extension. And so I'm trying to find a good sort of counter example to corollary 13. I want to find, what do I want to find? I want to find an infinite extension which has a number which is not algebraic. This is, I'm not liking this. Infinite extension. I think the reals over the rationals. So like the reals over the rationals, this is not a finite extension. Like the reals are not a finite dimensional vector space over the rationals. It is a difficult question to ask what the basis is of the real numbers with respect to the rational numbers. That's a whole other can of worms, but those bases, whatever they are, they're infinite, okay? I forget the name for them at the moment. I'm thinking Schroeder, but I could be wrong. Anyway, so, all right, so like, of course, pi is an element of the reals, right? And pi not algebraic over q. So, I mean, here's an example of an infinite extension where you're extending things which aren't necessarily algebraic.
Yeah.
But in contrast, right, so here's a positive example, like complex numbers over the real numbers, right? So the degree of the complex numbers over the real numbers is 2, right?
Yeah.
Because complex numbers are nothing more than the real span of 1 and I, right? And of course, up to isomorphism, as we have discussed ad nauseum, it's this guy, right? But the funny thing is, if you believe in corollary 13, every complex number is algebraic over the reals. And here's how. A plus IB is algebraic over the reals. There are two cases. If b is equal to 0, then you can take minimal polynomial of x just equal to x minus a. In other words, if the imaginary part's 0, that's just straight up. It's degree 1. It's actually a real number, honestly. Now, if b is not equal to 0, then you can make the minimal polynomial as follows. X minus a quantity squared plus b squared. That is a polynomial which takes a plus or minus ib as its 0. And it's irreducible over the reals.
Okay.
But this is arbitrary. These are the two cases. So every complex number is algebraic over the reals because this is a finite extension. So it is really, corollary 13 is saying something really quite profound in some sense. I mean, it's easy to kind of like gloss over it and not appreciate like how cool that result is. Because you've asked this question before, right? Like,
No, it's because like you think when I read it, extension of f, and if that extension is finite, then it's just all algebraic. Because the proof is, like, it's just like, what? Like, that doesn't make sense. But it's like, because alpha is in k, and f of alpha is a subspace of k, and we know that that's finite, this has to be less than finite.
Right.
Therefore,
Yeah, it's like
f alpha is algebraic over all of f.
yeah.
So we're not saying that we're not saying k is algebraic. No, wait. We are saying
K is algebraic over f.
Because
F
alpha is finite over f.
Right. But alpha is arbitrary. So we've shown that every number in K, since it sets up a subspace of K, that subspace has to be finite. And since that subspace is finite, that says that, that the number we're extending by is algebraic.
Yeah.
But since the number is arbitrary, we have that extension is an algebraic extension. So this example, this is an example of examples, okay? This example here is a, so check this out here. So let f be, I have skipped over this example in previous times I've taught this course, much to my own ashamedness, because this example is important and it is referenced a lot from this point on. Anyway, but it's also really nice. So let f be a field of characteristic not equal to 2. So characteristic 2 is an annoying, it's its own annoying set of problems, all right? So for example, any characteristic 0 field certainly fits the bill here. And let K be an extension of f of degree 2. All right. And next, he says, let alpha be any element of K not contained in F. All right. So that would be like case B not equal to 0 in my previous sub-example. Yeah. He says, by the proposition above, alpha satisfies an equation of degree at most 2 over f. Right? This cannot be degree 1, since alpha is not an element of f by assumption. It follows that the minimal polynomial of alpha has to be a monic quadratic of the form. Essentially by the previous corollary, or proposition 12, which way we want to look at it, alpha over f of x has to be equal to x squared plus bx plus c. All right. And since more than this, notice that we have f is a subset of f alpha, which is a subset possibly equal to k, right?
Yes.
But we already know that the dimension of k over f is 2, right? And this is not equal to f. So you have a two-dimensional vector space. You've got a subspace which is not one-dimensional. What is your choice? It's either 2 or 0, but 0 is not allowed.
Yeah.
So because it's between here and here. So this implies that, I thought I already said that, but, well, it implies that k is equal to f of alpha is what it gives us, right? Because it has to be the whole thing since it's a subspace of dimension 2. Mm-hmm. All right. And he says, the roots of this quadratic equation can be determined by the quadratic formula, which is valid for any field of characteristic not equal to 2. In other words, if we set x squared plus bx plus c equals to 0, I can do completing the square using field operations. Let's think about that. So I do first x plus b over 2. See right there, that's why characteristic 2 fails. Because in characteristic 2, there's no half. So not available. But any other field with characteristic not 2, that means 2 has an inverse, so 1/2 makes sense. And of course, when you square this, you get back, as you know, everything except for, well, we have to subtract b squared over 4, right? And then this gives us, x plus b over 2 squared equals to b squared minus 4c over 4, which gives us x is equal to minus b over 2 plus or minus the square root of b squared minus 4c. I'll put the 2 outside the root over 2. Where this is just notation, all right? Square root of b squared minus 4c is equal to a number such that the number squared is equal to b squared minus 4c, right?
Ladies and gentlemen, quadratic form.
Right. As he said, it's, well, I should be a little bit more, another way to say this is, this is the way he says it is a little bit better than this. He says this is solution of x squared minus b squared minus 4c. Now, he says that I'm sorry, I'm not sure I'm organizing his argument as I mean, if you read the book, of course, it's in logical order. I sometimes miss a sentence or something as I'm working here. But so the question though is, so we're assuming that alpha is not in F, right? Yeah. So like, for example, if you had x squared minus 4, this wouldn't work, you know? We need to know that the square root of b squared minus 4, say, let me say it this way. Okay, notice that if the square root of b squared minus 4c was equal to like Pac-Man squared for Pac-Man and F, then we're out of luck, because then that would mean that the the minimal polynomial over F would factor as x minus Pac-Man. Well, excuse me, x plus b over 2 minus Pac-Man, x plus b over 2 plus Pac-Man. And then that would be bad, because then, then our minimal polynomial is not irreducible. Oops. Okay, so it must be the case, by assumption that this is the minimal polynomial, right, that, and again, that alpha is not in F, it must be the case that square root of b squared minus 4c is not equal to the square of an element in F. So, long and short of this is that square root of, so the
Square root of Pac-Man.
I should actually just say I should just put Pac-Man here.
Yeah.
Sorry. So the square root of 4, so this means that, so this not being, I can't say words at the moment. B squared, I get a certain number of hours I'm allowed to lecture in a day before I start sounding like an idiot. And sometimes, yep. So there we go. Like that is what, we cannot have b squared minus 4c to be a square of a field element. Otherwise, it contradicts this being, alpha being in K, which is not in F.
Yeah, it makes minimal polynomial
Right.
go away.
But what this also means, right, is that we can look at K as as F extended by what? As extended by the square root of b squared minus 4c. Yeah, there you go. All right, let me. And he has a paragraph that, shows this for sure. If you look at the bottom of page 522, I'm not going to try to say that because I'm not sure it'll come out right. Anyway, here's the point though: is it follows that any extension K of degree 2 is of the form F adjoin the square root of D, where D is an element of F which is not a square in F. And conversely, every such an extension is an extension of degree 2 of F. For this reason, extensions of degree 2 of a field F are called quadratic extensions of F. So, anyway. So there will come a time we need this. I'm just putting it out there. So next up is theorem 14. All right. And theorem 14 is one of my favorites. Well, let's take a little 5-minute break and then start again.